Where did the direction of time come from? Hyperdecoherence and information gauge theory. Imagine two events in front of you. First, you press a button. A moment later, a light turns on. Without hesitation, we say that pressing the button was the cause, and the light turning on was the effect. The cause belongs to the past. The effect appears in the future. It seems so obvious that we rarely feel any need to question it. But what if, at the deepest level of the universe, that order has not yet been decided? What if the process in which the button is pressed before the light turns on, and the process in which the light turns on before the button is pressed, are not simply two alternatives whose true order is hidden from us? What if the order itself has not yet settled into a single reality? Of course, this does not mean that your future self can send today's version of you the winning lottery numbers. The real question is not whether science has discovered time travel. It is something far more fundamental. Is the rule that a cause must come before its effect built into the universe from the very beginning? Or does it emerge only after a deeper world of information has organized itself into the form we recognize? In 2026, James Hefford and Matt Wilson published a remarkable paper connected to this question. Its title was Decoherence to Quantum Theory from a Causally Indefinite Post-Quantum Theory. Their work showed mathematically how standard quantum theory could emerge from a higher-order quantum world in which causal order is not globally fixed. To understand the significance of this result, we first need to begin with a more familiar idea: decoherence. In quantum mechanics, an electron or a particle of light does not have to follow only one possibility. The possibility of being here and the possibility of being there can coexist while maintaining a delicate relationship with each other. But in everyday life, we never see a car occupying two cities at once. We never see a baseball flying along two clearly visible paths at the same time. Decoherence helps explain why. A quantum system is never perfectly isolated. It interacts continuously with its surroundings. As it becomes entangled with the environment, the subtle phase relationships among its different possibilities become practically impossible for us to observe. Imagine one person singing in a quiet room. You can hear the pitch, the rhythm, and even the faint tremble in the singer's voice. Now place that singer in a crowded square where tens of thousands of people are speaking at once. The voice has not been erased from the universe, but its precise relationship to all the other sounds has become impossible for you to track. Quantum decoherence is something like that, and this leads us to a deeper possibility. If the classical world emerges from the quantum world, could the quantum world itself emerge from an even deeper level of reality? The proposed transition from a theory beyond quantum mechanics to standard quantum theory is called hyperdecoherence. Ordinary decoherence takes us from the quantum world toward the classical world. Hyperdecoherence would take us from a post-quantum world down to the standard quantum world we know. It is an attractive idea, but it soon encounters a formidable barrier. In 2018, Lee and Selby proved a powerful no-go theorem. They showed that if a post-quantum theory satisfies two seemingly natural principles at the same time, then it cannot reduce to standard quantum mechanics through a decoherence-like process. The first principle is causality. A choice made in the future must not alter the statistics of events already observed in the past. The second is the essential uniqueness of purification. A state that looks mixed or incomplete can sometimes be understood as part of a larger pure state. The purification principle says that this larger description is essentially unique, apart from reversible changes made only to the environment. The conclusion of Lee and Selby was severe. If we insist on preserving both causality and unique purification, then we cannot simply place a deeper physical theory above quantum mechanics and recover quantum mechanics through hyperdecoherence. So is quantum mechanics truly the final layer? Or have we treated one of these principles as more fundamental than it really is? Hefford and Wilson chose a path in which processes, rather than states, become the more fundamental objects. In standard quantum mechanics, we have quantum states, and quantum channels transform those states. It is rather like having a letter and a postal route that carries the letter from one place to another. But in higher-order quantum theory, the postal route itself can become the object being transformed. We can imagine a higher-level operation that takes one way of transmitting a quantum state and turns it into another way of transmitting it. In quantum information theory, such transformations are called supermaps. The name sounds difficult, but the idea is simple. A supermap does not merely change a state. It changes the process that changes the state. It is not just a change of words or sentences. It is a change in the grammar that determines how sentences can be formed. The theory used in the paper is called QBox. It is built from these higher-order quantum processes. Its systems are not merely particles. They are quantum boxes with both inputs and outputs. And when several boxes are combined, the theory does not require every box to be assigned one fixed global time order in advance. Event A may occur before event B. Event B may occur before event A. More surprisingly, there may be processes that cannot be reduced to an ordinary classical mixture of these two possibilities. That does not mean faster-than-light communication becomes possible. The non-signaling principle can still prevent two distant observers from transmitting messages by using entanglement alone. What is abandoned is not every form of causal discipline, but the assumption that the entire universe must come with one predetermined timetable attached to all events. So how can ordinary quantum mechanics emerge from this unfamiliar world of QBox? Hefford and Wilson constructed a special transformation that completely randomizes one part of a quantum box while leaving the other part intact. Roughly speaking, the lower input-like degree of freedom is turned into a state so thoroughly mixed that it can no longer distinguish any information. The upper, future-directed part remains accessible. Imagine a transparent sheet with writing on both sides. At first, you can read the front and the back. Then the back is covered by white noise until its writing can no longer be recovered. You can now use only the information on the front. The entire world has not vanished. What has changed is the range of processes available to the observer. The authors showed that this transformation satisfies the important conditions expected of hyperdecoherence. Applying it twice produces no further change. The transformation itself does not send information from the future into the past. A loss of information does not mysteriously turn a mixed state into a perfectly pure one. And a maximally disordered state remains maximally disordered after the transformation. Most importantly, when the systems and processes that survive this transformation are collected together, their complete structure corresponds to standard quantum channel theory. This is not merely a similarity between a few probabilities. The rule for connecting processes in sequence, the rule for placing processes side by side, and even the identity operation that represents doing nothing, all match the structure of ordinary quantum theory. That is the central result of the original paper. A higher-order quantum theory, without a fixed global causal order, can, under an appropriate hyperdecoherence map, produce standard quantum theory. So what distinguishes this result from earlier work? Previous studies using process matrices had already shown that locally valid quantum processes can exist without a predetermined global causal order. But they did not construct the same explicit bridge showing how ordinary quantum theory could be selected from such a world. Earlier proposals, such as density cubes and quartic quantum theory, also attempted to describe interference beyond standard quantum mechanics. Yet some of them faced difficulties in defining composite systems and consistent rules for combining processes. QBox is constructed from quantum channels and supermaps already used in quantum information theory, so its operational meaning is comparatively clear. The new paper also does not claim that the Selby theorem was wrong. Instead, it reveals the precise boundary of that theorem. In QBox, a mixed process can be extended into a larger pure process, but that extension need not be unique. One of the central assumptions of the no-go theorem no longer holds, and a new path becomes possible. This also forces us to reconsider what we mean by purity. In a higher-order theory, a quantum channel itself can function as a state. When our choice of fundamental object changes, the definition of a pure state changes with it. Is purity an intrinsic property that the world possesses by itself? Or is it relational, depending on what we decide to call the system and what we place outside it as the environment? Time and causality may raise a similar question. We tend to imagine time as a vast river, carrying every event from the past toward the future. The river exists first, and the events of the universe float upon it like boats. But perhaps the river does not come first. Perhaps countless informational relationships among events become organized in a particular way, and only then do we call the resulting order the flow of time. Time may not be the stage on which events are placed. It may be the order in which events can be read. A library may contain every page of every book, yet we take out one volume and read it from the first page to the last. Hyperdecoherence resembles a rule that allows us to turn the pages in only one direction. Past and future may separate, not because all other pages are absent, but because the observer's access to the library is restricted. Yet the original paper has an important limitation. Hefford and Wilson showed that a mathematical door to hyperdecoherence can exist, but they did not explain how that door physically closes. Their construction does not tell us how quickly the transformation occurs, what physical field randomizes the hidden degrees of freedom, at what energy scale the effect becomes important, or what traces might remain before the system reaches ordinary quantum theory completely. There is a door, but there is no clock. This is where an information gauge, or IG, interpretation can be proposed. From this point onward, we are no longer describing a result proven in the original paper. We are exploring a new hypothesis that tries to turn its static map into a dynamical theory. In the IG picture, information following different paths does more than arrive at the same destination. It can accumulate an invisible phase depending on the path it has taken. Phase is like the position of a wave within its cycle. Two waves may arrive at the same point, but if their cycles are aligned, they reinforce each other. If their cycles are out of step, they weaken each other. Now imagine one causal path in which event A precedes event B, and another in which B precedes A. Joining the two paths forms a closed causal loop. After information travels around that loop and returns to its starting point, a small phase difference may remain. This residual, path-dependent phase is what we call information holonomy. The word holonomy may sound unfamiliar, but the underlying image is surprisingly intuitive. Suppose you carry an arrow across the curved surface of Earth, keeping it as parallel as possible while walking along the sides of a large triangle. When you return to your starting point, the arrow may no longer point in its original direction. The difference reveals the curvature of the surface. You cannot determine it from the starting point and ending point alone. You must know the path. Holonomy is the memory of that path. The IG proposal asks whether something similar can occur in the relational space of information. When information travelling through different causal orders meets again, the phase left by those paths could determine how strongly the two causal orders interfere. But a real observer cannot control every microscopic fluctuation of the information gauge field. The holonomy phase may tremble slightly. As those fluctuations accumulate, the delicate relationship between different causal orders begins to blur. At first, the two orders may interfere clearly, but as time passes, or as the observer's resolution becomes coarser, the interference gradually weakens. In this picture, hyperdecoherence is not an instantaneous deletion. It becomes a flow with a finite rate. Post-quantum residuals may be present at first and then fade away. Like the sound of a distant bell, the signal does not disappear all at once. Its amplitude falls until it passes below the threshold of our hearing. So what would this theory predict? For beautiful philosophy to become science, it must tell us what to measure and what result would show that the idea is wrong. The first possible signature is a tiny residual deviation from standard quantum probabilities. If hyperdecoherence is not infinitely fast, then traces of the higher theory should remain before the system reaches the standard quantum limit. We could ask whether these deviations decrease in a common systematic way as the interaction time or observational scale changes. The second signature concerns causal non-separability. Researchers can construct tests that distinguish an ordinary classical mixture of A before B and B before A from a process that cannot be separated into those two causal orders. Such a test is called a causal witness. Just as a witness in a courtroom reveals evidence of an event we did not directly see, a causal witness reveals a non-classical temporal structure hidden inside a quantum process. If the IG proposal is correct, the non-classical part of the witness signal should weaken as the information holonomy fluctuates. At some point, a particular witness may no longer detect causal non-separability. This would not necessarily prove that every non-classical feature has vanished. The signal may simply have fallen below the sensitivity of that test. The third possible signature is higher-order interference. Standard quantum mechanics allows interference between alternative paths. But if three paths are opened and closed in a carefully controlled sequence, a properly constructed third-order interference term should vanish in ordinary quantum theory. If a post-quantum residual can generate higher-order interference, a tiny third-order signal might appear and then fade under hyperdecoherence. This point requires special caution. The original paper did not prove that QBox actually produces higher-order interference. This is an additional, testable hypothesis introduced by the IG extension. If experiments fail to find such a signal, the hypothesis must be restricted or abandoned. The fourth signature is more specific. Suppose the information gauge phase is subject to Gaussian noise, the familiar statistical pattern produced by many small random fluctuations. In that case, a mode carrying twice the information charge should decay 4 times faster, while a mode carrying 3 times the charge should decay 9 times faster. The hierarchy would be 1, 4, 9, the square of the information charge. It is much harder for ordinary instrumental noise to reproduce the same square law pattern across several independent charge sectors. The fifth and most important signature is shared behavior across different experiments. A deviation in quantum probabilities, the decay of a causal witness signal, and a possible higher-order interference term should not change at unrelated rates. If they arise from the same information holonomy, they should share the same decay envelope and the same phase rotation. The orientation of the causal loop also matters. Reversing the loop should reverse the sign of the average phase, just as walking around a curved route, clockwise and counterclockwise, reverses the direction of the geometric effect. If this orientation dependence appeared across several observables at once, we would have a reason to suspect not just ordinary noise, but a common geometrical structure of information. Finally, the IG model interprets standard quantum mechanics as a stable fixed point. A fixed point does not mean one frozen physical state. It means a form of law toward which many different starting points flow. Rain falls on many parts of a mountain. At first, the droplets move in different directions. Then they enter valleys, join streams, and eventually flow into the same river. Their starting points differ, but downstream they all obey the structure of the same current. In the same way, the deep high-energy world may contain many post-quantum processes. But at low energies, or under coarse observation, they may all flow toward the stable river of standard quantum theory. From this perspective, quantum mechanics may be universal, not because it is the most fundamental possible theory, but because it is the most stable form into which many deeper possibilities eventually flow. Yet this beautiful picture faces a decisive test. Randomizing a single information phase may not erase every post-quantum degree of freedom. Some neutral modes may not respond to that phase at all. Unless an additional mixing process removes those modes, standard quantum mechanics will not be the unique final theory. If a post-quantum residual remains even after long times or extreme coarse graining, it might point toward physics beyond quantum mechanics. But it would also show that the present IG fixed point model is incomplete. A good theory must tell us in advance what could bring it down. Now let us return to the button and the light. We say that the button was pressed and then the light turned on. The cause came first and the effect followed. In our world, this rule works with astonishing precision. But at a deeper level, the order of cause and effect itself may be one of several possibilities. What we call time may be the most stable order left behind after the phases of many causal paths have blurred and observers can access only one direction of process. Does time truly flow, or is it the trace left behind after information has been ordered and other possibilities have faded from view? We do not yet know the answer. Hefford and Wilson showed that a mathematical door may exist from a higher-order quantum theory without fixed causal order to ordinary quantum theory. The IG proposal suggests that fluctuations of information holonomy could close that door at a finite rate, leaving small echoes before it shuts completely. Those echoes might appear as tiny deviations in quantum probabilities, traces of causally non-separable order, or higher-order interference forbidden by standard quantum theory. And if different signals fade at the same rate and display the same orientation-dependent phase, we could begin to ask whether a single geometry of information lies behind them all. Science begins by imagining what cannot yet be seen, but imagination becomes science only when it tells us how it could be proven wrong. If a world before quantum mechanics truly exists, it may not announce itself with a thunderous voice. It may survive only as a faint resonance within the direction of time we take for granted, within the gap between cause and effect, and within the almost perfect laws of quantum theory. We are only beginning to listen for that echo. If you found today's content useful, please subscribe and hit the like button. This has been ThothSaem's Science Catch.